Okay. So, hi everyone. So first of all, let me know whether audio and video are clear or not. Yes or no here? So first of all, let me know whether audio and video are clear. Is audio and video are clear here? Yes or no? So is audio and video clear? Give some comments in chat box here so that we can start the topic today. Is audio and video clear? Hello? Okay. Okay. So I hope it is clear here. I hope audio and video everything is clear. Okay. So from today onwards, we are going to start concept through questions here. We are going to start concept through questions. So that is CTQ. So concept through questions. So we are going to analyze the question and what is the concept behind that question. So we are going to study both here, concept and also as well as how to solve the question or problem, given problem. Okay. So those things we are going to see from today onwards here, from today onwards. So EMT class will start every day at 4 p.m. here, same timing. Okay. And also from tomorrow onwards, I am going to deal with analog electronics also. So it is going to start at 10 a.m. here in the morning. Okay. So that is also CTQ. That is also concept through questions only. Okay. Okay. Yeah. So let's start here. Let's start today's session. Okay. So here I have given you a problem here. So see this problem. So what is this problem here? See here what they have given. They have given that here the charge distribution within a unit sphere, of radius or less than or equal to 1, that means the radius of the sphere is from 0 to 1. Okay. So radius is r less than or equal to 1. So is given by V is equal to minus 10 into r power 6 by pi epsilon into sine theta volts. Okay. So then determine the total charge, Q total within the unit sphere, and they have given a hint, that is use spherical coordinate system. Okay. So first see here, they have given the charge distribution within a unit sphere. The charge distribution within a unit sphere of radius r less than or equal to 1 is given by, see, sorry here, in this question it is not charge distribution here, it must be potential distribution here. Okay, it is not charge distribution, so it must be potential distribution here. So question framing is wrong. Okay. So note down this here. Okay. So they have given the potential distribution within a unit sphere of radius r less than or equal to 1 is given by V is equal to minus 10 into r power 6 by pi epsilon sine theta volts. It is potential distribution here, not charge distribution, it is potential distribution. Okay. So that means if you take a unit sphere here, if you consider a unit sphere, okay. So if you consider a unit sphere, so its radius is equal to 1 here, So if you consider an unit sphere, Okay, so within that unit sphere they have given the charge distribution, potential distribution. So the potential distribution they have given as V is equal to what? V is equal to minus 10 into r power 6 divided by pi epsilon into sine theta volts, sine theta volts. So this is the potential distribution they have given, and they are asking what is the total charge. That means within this unit sphere you are having some charge distribution here. Within this unit sphere you are having some charge distribution, and this charge distribution, whatever the charge that is distributed within this unit sphere, is producing some potential, within this unit sphere. And how that potential is varying, that is given by this expression. Understood here? So you are having an unit sphere. Within that unit sphere you are having some charge distribution, yes or no, right? Okay, so that charge distribution is producing the potential, and how that potential is distributed within the unit sphere, is given by this expression, yes or no? So this is the expression for what? For r less than or equal to 1. That means inside the unit sphere, this is how the potential is distributed, and this potential we got this potential because of what? Because of the charge, that is distributed within the unit sphere, So this charge distribution is the cause for this potential distribution within the unit sphere. Understood? Okay, now what they are asking is what is the total charge, that is present within this unit sphere. So they are asking what is the total charge, that is present within the unit sphere, right? Okay, so you are having unit sphere. Within that unit sphere some charge distribution is present, and the charge distribution is producing some potential, yes or no? Okay, so that potential is also distributed throughout the volume of the sphere, and how that potential is distributed is given by this function, right? Okay, so they have given the potential distribution, and from this potential distribution they are asking to determine what is the total charge, that is present within this unit sphere. So this is the question here, okay. See, whenever they are asking the total charge here, that is present within the volume of the sphere, okay. So generally what we remember is from Gauss law here. So immediately what strikes our mind is Gauss law, because Gauss law is going to relate, yes or no? So what is Gauss law here? Gauss law is going to relate between what? The electric flux and charge. Yes or no? It is going to relate between electric flux and charge. Yes or no? Okay. So from Gauss law here, we know that the electric flux that is leaving any closed surface, must be equal to what? Must be equal to the total charge, that is enclosed by that closed surface, divided by what? Divided by epsilon, right? Okay, so this is nothing but Gauss law. So what Gauss law says here? The electric flux that is leaving any closed surface here, must be equal to what? Must be equal to the total charge enclosed by that closed surface, or you can say net charge or total charge enclosed by that closed surface, divided by what? Divided by epsilon. Okay, so if you know the electric field here, understood, then you can perform this integration, and from this you can determine what? You can determine the total charge. But here they have not given the electric field here, distribution, yes or no? But instead what they have given here? They have given the potential distribution. Potential distribution, right? Okay, so see here, wait. Okay, so I am writing here, so V is equal to minus 10 into r power 6 sine theta divided by pi epsilon. Okay, so from Gauss law we know that the electric flux that is leaving any closed surface must be equal to what? Must be equal to the total charge enclosed by the closed surface divided by epsilon. Right. Okay. So what do you mean by electric flux here? If you consider any closed surface here, if you consider any closed surface, suppose the electric field lines are leaving this closed surface here. Suppose let us assume the electric field lines are leaving this closed surface. See, if the electric field lines are leaving this closed surface means, okay, there must be a cause, there must be a cause of these field lines, right? There must be a cause of this electric field lines within the volume, yes or no? So inside this closed surface there must be a source of this electric field lines, right? Okay, so what is the source of this electric field lines here? Is nothing but what? Is nothing but charge, is nothing but the total charge, or you can say simply net charge here, net charge. Understood? See, if there is no net charge, within the inside the closed surface, then there will be no electric field lines. Yes or no? Okay, so the number of field lines that are leaving this closed surface is called as electric flux here. And what is causing this electric flux? The cause for this electric flux is nothing but what? Is nothing but the charge that is enclosed by this closed surface. Right. Okay, so that's what we have written. And the number of field lines that are leaving this closed surface is also going to depend upon what here? Is also going to depend upon epsilon. That means it is also going to depend upon medium parameter. Right, it is also going to depend upon medium parameter. So that means if you change the medium here inside this closed surface, if you change the medium, then the number of field lines that are leaving the closed surface is also going to change. See, if I consider this medium as air medium, okay, so whenever it is air medium, the number of field lines that are leaving is something, okay, and if I change the medium to glass medium, then the number of field lines that are going to leave the closed surface is going to be different. Understood? Okay, it is not going to be same. So that means the number of electric field lines that are leaving any closed surface, that is called as electric flux, must depend upon what? It is going to depend upon the total charge, and also it is going to depend upon the medium in which that charge is present. The medium in which that charge is present. So on these two parameters it is going to depend. Right? Okay. Okay. Yeah. So now so now in order to determine the total charge within the unit sphere, in order to determine the total charge within the unit sphere, you have to know what? You have to know electric field. You have to know electric field. So if you know the electric field, then you can determine the total charge that is present within the closed surface, or within the volume of the sphere, or within the unit sphere. All are same here. All are same. Right? Okay. So, but they have not given the electric field expression here. They have given what? Instead, they have given the potential distribution. Right? Okay. So, from this potential distribution here, if we try to determine the electric field, okay, so then from this expression, we can determine what? We can determine the total charge. Yes or no? Okay. So, from this given potential distribution, we try to determine the electric field. Once you know the electric field, then you can easily determine the total charge. Okay. Okay. Yeah. So they have given V here. They have given the V, that is potential. Okay, and we have to determine electric field. So what is the relation between electrostatic field? This is electrostatic field here. What is the relation between the electrostatic field and the potential? Electrostatic field and electrostatic potential. What is the relation here? We know that E is equal to what? E bar is equal to minus gradient of V here. E bar is equal to minus gradient of V. Right? Okay. So the electric field and potential are related through this relation. So this relation is valid only for static fields here. Whenever you are dealing with static electric field, then only this relation is valid. That is E bar is equal to minus gradient of V. Okay. So the units are nothing but volt per meter. So from this relation here, since we know potential, from this relation you can determine what? You can determine electric field. Now here, see here, it is very simple to understand this relation here. See here. Now here, gradient of V here, gradient of V. Okay, so what do you mean by gradient of V here? See, gradient of V is nothing but what? Is nothing but a vector quantity. if you perform gradient operation here, if you perform gradient operation on any scalar function, the resultant is nothing but a vector quantity. And what this gradient will represent here? The gradient will always points in the direction of maximum increase of the scalar function. That means in which direction the scalar function is increasing maximally. So it always points in that particular direction. So what I mean here is gradient of V will always points in the maximum increase of potential direction. Understood? So maximum increase of potential direction means it always points from where to where here? From lower potential to higher potential. It always points from lower potential to higher potential. Why here? Whenever you are calculating the gradient, okay, the resultant of gradient is a vector quantity, and that vector is always going to point in a direction in which this scalar function is increasing maximally. Okay, so it is going to point in a direction in which the potential is increasing maximally. Here the scalar function is nothing but potential. So gradient of V is going to give you a vector that is going to point in a direction in which this potential is increasing maximally. It is increasing maximally. So that means it always points from where to where here? Lower potential to what? Lower potential to higher potential. It always points from lower potential to higher potential, right? And we know that this electric field here, will always points from where to where here? The electric field will always points from where to where? It always points from higher potential to what? It always points from higher potential to lower potential, right? It always points from higher potential to lower potential, and hence we have put here minus sign. So that's why we have put here minus sign, because gradient of V is a vector quantity that is going to point from lower potential to higher potential, whereas electric field is a vector quantity that is going to point from higher potential to lower potential, right? Higher potential to lower potential. So whenever we are equating LHS must be same as RHS, and that's why we have put here minus sign, right? Okay, so this is the relation between electric field and potential. And also I have told that this relation is valid here. This relation is valid only for what? Only for static fields. Right? Okay, so it is valid for only electrostatic fields here. See, why means if you take curl on both sides here, what you are going to get? Curl of E bar is equal to what? Is equal to minus of curl of gradient of V. So curl of gradient of any function here, curl of gradient of any scalar function is always equal to what? Is always equal to 0. So that means del cross E bar is always equal to what? Is always equal to 0. See, this del cross E bar must be always equal to 0 in case of what? In case of static fields here. In case of only static fields. It is true only in case of what? Only in case of static fields, right? Okay, so here this electrostatic field, we call it as what? We call it as conservative field. So once we enter into time varying case, we are going to see that del cross E bar is not equal to 0 here. There you are going to get whenever we enter into time varying fields here. That means whenever we are studying Faraday's law, there we are going to see that curl of E bar is not equal to 0. So that means electrostatic field is not a conservative field. Okay, so that means here you cannot write E bar is equal to minus gradient of V. So this relation is wrong here. This relation is wrong in case of what? In case of time varying fields. This relation is valid only in case of what? Only in case of static fields here. So if the field is conservative, one thing remember, if the field is conservative, then you can represent that field. In terms of what? In terms of gradient of some scalar function. So any conservative field here, you can represent it as what? Gradient of some scalar function, right? Okay, so that's why this relation is valid here. This relation is valid only in case of what? Only in case of static fields. Okay. Okay, yeah. So coming to the question here, so whenever we are dealing specifically with the potential na, so at that time I will explain this again here clearly. Okay. Okay. At that time we will see all these things. Okay, whenever I am dealing with the potential specifically, so at that time once again we are going to deal with all these things in a in depth manner here. Okay. Okay. Okay, yeah. So from this relation you have to determine what we know potential, we have to determine what, we have to determine electric field, right? Okay. So now they have said, they have given a clue here in the question, they have given that they have given a hint here. What is the hint they have given? Use spherical coordinate system. So this is the hint they have given. Yes or no? Why means here the potential distribution here, the potential distribution is given in terms of what? In terms of spherical coordinates, right? Okay. So here r and theta are nothing but what? Are nothing but spherical coordinates. So they have given the potential distribution in terms of spherical coordinates. That's why they have given the hint to use what? To use spherical coordinate system in order to solve this problem, right? Okay. Okay, yeah. So this is potential, we have to determine the electric field. So E bar is equal to minus gradient of V. So that means you have to expand, or you have to express this gradient of V in which coordinate system here? In spherical coordinate system, because they have given the potential in terms of what? In terms of spherical coordinates, right? Okay, so that's why you have to expand this gradient of V in terms of what? Spherical coordinate system. So now I will tell you a trick here. I will tell you a trick how to calculate the gradient in spherical coordinate system or in cylindrical coordinate system. I will tell you a trick here. See here, coming to spherical here, So in spherical coordinate system, what are the differential lengths we are having here? What are the differential lengths we are having? The differential lengths we are having are dr, and then dr is the differential length along r, right? Okay, and another one is the differential arc length along theta. So the differential arc length along theta is nothing but r d theta, and the differential arc length along phi, so that is along horizontal circle, so that is nothing but rho d phi, and rho is nothing but r sin theta. So you can write it as r sin theta d phi. So these are the differential lengths here. These are the differential lengths in spherical coordinate system. Okay. Whereas in cylindrical coordinate system, what are the differential lengths here? What are the differential lengths? The differential length along rho is nothing but d rho. Differential length along phi is nothing but rho d phi. Differential length along z is nothing but dz. So I am explaining how to write this gradient, whether it is in spherical coordinate system or in cylindrical coordinate system. That's what I am explaining here, right? Okay. Okay, yeah. So here gradient of V. So I am expanding this gradient of V in spherical coordinate system. So here you are having radial component AR cap plus here A theta cap plus here A phi cap, Okay. So now in the first term, differentiate the potential with respect to R. So that is dou V by dou R. And in the second term, differentiate the potential with respect to what? With respect to theta. So then you are going to get what? Dou V by dou theta. Next, differentiate the potential with respect to phi. So that is dou V by dou phi. Why I am using partial differentiation here? Because the potential is not only a function of R, it is also a function of what? Theta. So it is a function of more than one variable. So that's why I am using here partial differentiation, right? Okay. Okay, yeah. So dou V by dou R, AR cap plus dou V by dou theta, A theta cap plus dou V by dou phi, A phi cap. Now here the coefficient of dr here. What is the coefficient of dr? Is nothing but 1. So write down the coefficient of dr in the first term in the denominator here. So that is 1 by 1. and write down the coefficient of d theta, that is r, in the denominator of this term. So that in the denominator you have to write 1 by r, and here also write down the coefficient of d phi. The coefficient of d phi is nothing but r sin theta in the denominator of this term. So that is 1 by r sin theta, 1 by r sin theta. So this is how you have to write what? You have to write the gradient in case of what? In case of spherical coordinate system. Understood? Okay. Okay. Yeah. Similarly, if you want to write cylindrical coordinate system, if you want to expand gradient of v in cylindrical coordinate system, how you can do that here? Tell me. So gradient of v is equal to what? Is equal to, so first write down a rho cap term plus what? Plus a phi cap term plus what? Plus az cap term plus az cap term. Okay. Okay. Yeah. So now see here. So what I have told here? So write down here dou v by dou rho, differentiate potential with respect to rho, and write the coefficient of d rho, write the coefficient of d rho in the denominator, so you will get 1 by 1. Okay, and here differentiate with respect to phi, differentiate the potential with respect to phi, so dou v by dou phi, and here in the denominator write down the coefficient of d phi, so write down the coefficient of d phi, that is 1 by rho. And in the third term, so differentiate the potential with respect to what? With respect to z, and write down the coefficient of dz in the denominator here, so you will get 1 by 1. So this is how you have to expand gradient in case of what? In case of spherical and in case of cylindrical. See, if you remember this differential lengths here, then it is going to be very, very simple here. See, whatever the topic you can take here, throughout this electromagnetics, this coordinate system, and the basics of vectors, right? Okay, so all these things are going to play a very important role here. So this gradient operation, divergence operation, curl operation, and basics of vectors, everything, each and everything, coordinate system, each and everything is going to play a very important role throughout this subject. Okay. Okay. So this is the way you have to express what? You have to express the gradient, whether it is in spherical coordinate system or it is in cylindrical coordinate system. So I hope it is clear here. Okay. So now here, coming to our problem here, we have to determine the electric field. That is our task, right? Okay. Okay. Yeah. So electric field E bar is equal to what? Is equal to minus of, okay, so electric field E bar is equal to minus of what? Minus of gradient of V, so that is equal to, tell me here, so minus of, okay, so gradient of V, so expand this gradient here, in spherical coordinate system, what you are going to get? Tell me. So here I am writing V here, V is equal to minus 10 into r power 6, okay, minus 10 into r power 6 by pi epsilon into sine theta. So this is the potential we are having. Okay, this is the potential expression we are having. So now determine gradient of V in spherical coordinate system. See, the first term, you have to differentiate this potential. With respect to what? With respect to R. So whenever you are differentiating this potential with respect to R, this sine theta will become constant or not? Yes or no? Sine theta is constant with respect to R. So first write down that constant term here. What are the constant terms? Minus 10 is constant, pi epsilon is constant, sine theta is also constant with respect to R. So I am writing that one here first, minus 10 by pi epsilon into sine theta. So what is left out? R power 6. What is the differentiation of R power 6? The differentiation of R power 6 is nothing but what? Is nothing but 6 into R power 5. 6 into R power 5. So this is AR cap component. Plus. Next, you have to differentiate the potential with respect to what? With respect to theta, and you have to multiply with 1 by r. You have to multiply with 1 by r. So here I am multiplying with 1 by r. Now try to differentiate this potential with respect to theta r. So whenever you are differentiating with respect to theta, this minus 10 r power 6 by pi epsilon is constant. So I am writing that constant term here. So minus 10 r power 6 by pi epsilon will become constant with respect to theta. So now differentiation of sine theta. Differentiation of sine theta is how much here? Is nothing but cos theta a theta cap. Right. Okay. Next. Next plus 1 by r sine theta. So you can write 1 by r sine theta. Okay. So dou v by dou phi. That means you have to differentiate this potential. You have to differentiate this potential with respect to what? With respect to phi. But here this potential distribution is independent of what here? Is independent of phi or not? It is a function of what? Only r and theta. It is independent of phi. So if you differentiate this potential with respect to phi, what you are going to get? You are going to get 0. You are going to get 0. Right? Okay. You are going to get 0. So that means the overall gradient of phi. So E bar is equal to, so what is the expression you are going to get? So multiply with minus here. So here you are having minus into minus will become plus, and here minus and here minus will become plus, and this term is 0. You are having only AR cap component and A theta cap component. Right. Okay. So write down that here. So electric field is equal to, so everything will become plus here, because if you multiply with minus, everything is going to become, all the components are going to become positive. Okay. Okay. So write down here. So 10 by pi epsilon into sine theta into r power 5. So 6 is there. 6 into 10 is 60. So I am writing here 60 here. So 60 by pi epsilon into sine theta into r power 5 AR cap. Right. Okay. Next second term plus here r and here r power 6. So you will get r power 5. So you will get 10 into r power 5 divided by pi epsilon into cos theta a theta cap. Okay. So this is the electric field expression we got. So this is nothing but what? This is nothing but radial component. So I am calling this as ER here. And this is nothing but what? This is nothing but theta component. So I am calling this as E theta. Okay. So E bar is equal to what? Is equal to ER AR cap plus E theta A theta cap. So where ER is nothing but this term and E theta is nothing but this term. Okay. Okay. Yeah. So now here okay. So this is how you can write electric field. Right. Okay. Okay. Now, okay, yeah. So finally we have determined electric field. The electric field from the given potential distribution. Okay. So now we can use Gauss law now. Okay. So now we can use Gauss law in order to determine what? In order to determine the total charge. So the electric flux that is leaving any closed surface must be equal to what? Must be equal to the total charge enclosed by the closed surface divided by what? Divided by epsilon. So now we know electric field, and hence you can determine what? You can determine the total charge that is present within the unit sphere. Okay. Okay. Yeah. So now here this represents what here? You are having a unit sphere. So this is R equal to 1. Now let us consider a Gaussian sphere. Just above this unit sphere here. Okay, so this is Gaussian sphere. This is Gaussian sphere. It is just above the unit sphere, or I can say almost on this unit sphere. It is just above the unit sphere here. Okay, it is not touching the unit sphere, just above the unit sphere, such that for Gaussian sphere also you can consider the radius as what? The radius as 1. The radius as 1. So inside this Gaussian surface you are having what? You are having some charge distribution. So because of this there is an electric flux. There is an electric flux that is leaving this closed surface. Right? Okay. Okay. So now here you have to determine the electric flux that is leaving this closed surface, that is through this Gaussian surface. Here Gaussian surface is also, I am considering this as what? This is nothing but Gaussian surface. So that is, I am considering it as Gaussian sphere here. Gaussian sphere whose radius is almost equal to what? Almost equal to 1, and it is just greater than 1 here. Okay, just greater than 1. So this Gaussian sphere is almost present on the unit sphere here, on the unit sphere, right? Okay, okay, yeah. So now see here. So now the electric flux that is leaving the closed surface. So now you have to represent the closed surface here. See, what are the variables on the surface of the sphere here? What are the variables on the surface of the sphere? If you consider a sphere here, if you consider a sphere like this, let us assume this is a sphere. Okay, so if you consider a small differential area, on the surface of the sphere, so if you move on the surface of the sphere, what is going to vary here? R is not going to vary, right? Okay, that means the radius of the sphere is not going to vary. As you move on the surface of the sphere, the radius of the sphere is not going to vary. What is going to vary? Theta is going to vary and phi is going to vary. So that means theta means movement along vertical circle, phi means the movement along horizontal circle, right? Okay, so if you consider a small differential area on the surface of the sphere, what are the variables here? What are the variables? Theta is going to vary and phi is going to vary, but R will remain constant. Right? Okay, so that means what is the differential area you can write on the surface of the sphere? The differential area on the surface of the sphere, you can write it as what? What are the variables? Theta and phi. Understood? So what is the differential arc length along theta here? That is nothing but r d theta. And what is the differential arc length along phi here? That is nothing but r sin theta d phi. So this is the differential arc length along theta, and this is the differential arc length along phi. So if you multiply these two arc lengths, you are going to get what? You are going to get small differential area on the surface of the sphere. So we call this a small differential surface area with what? dA bar. And what is its direction here? See, r d theta is going to point along a theta cap direction. So cross r sin theta d phi a phi cap. A theta cap cross a phi cap will give you what? AR cap direction. So you are going to get r square sin theta d phi. A theta cap cross a phi cap is AR cap. So this is the small differential area on the surface of the sphere. Okay, what is the direction of this small differential area on the surface of the sphere here? It is going to point along which direction? AR cap direction. That means if you draw the normal, consider any small differential area on the surface of the sphere, and if you try to draw the normal on that small differential area, it is going to point along what? It is going to point along radial direction, that is in AR cap direction. Okay, okay, yeah. So so if I consider E bar dot dA bar, I am considering this small differential area here, that is nothing but dA bar. Then the flux through this small differential area, I can write it as what? E bar dot dA bar. Now if I want the total electric flux that is leaving throughout the surface of the sphere, then what you have to do? You have to integrate throughout the surface of what? Throughout the surface of the sphere. So throughout the surface of the sphere you have to integrate. So that's why I have represented it with closed surface integral. Understood? So what do you mean by this closed surface integral here? Here the variables are theta and phi. So you are considering the total surface of the sphere. That means you have to consider the total range of theta and total range of phi. right? Okay, so you have to integrate the variables on the surface of the sphere are nothing but theta and phi, and you have to integrate with respect to theta and phi over their full range, because you are considering the total surface of the sphere, right? Okay, so theta is equal to what? 0 to pi, and phi is varying from 0 to 2 pi. Phi is varying from 0 to 2 pi. So this is equal to q total divided by what? Divided by epsilon. Okay, so now this electric field is having radial component plus theta component. This electric field is having radial component as well as what? Theta component. And what is this differential area? Just now we have seen. Okay, what you are going to get? R square sine theta d theta d phi AR cap. Now now if you do the dot product here, if you do the dot product between these two, what you are going to get here? AR cap dot AR cap will become 1, A theta cap dot AR cap will become 0 or not, because A theta cap direction and AR cap direction both are what? Both are perpendicular to one another, and hence A theta cap dot AR cap will become 0. So finally if you do the dot product, between these two, okay, so only AR cap terms will get multiplied, this A theta cap term, A theta cap dot AR cap will become 0. Okay. Okay, yeah. So write down that expression here, what you are going to get. So theta is equal to what? Theta is equal to 0 to pi. Theta is varying from 0 to pi, and phi is varying from where to where here? 0 to 2 pi. 0 to 2 pi. So now consider only ER AR cap here. Why? A theta cap dot AR cap will become 0. Okay, so what is left out? You are going to have ER into R square sine theta d phi. Okay, so what is ER here? What is ER? So we have determined that here ER. So the expression for ER is nothing but what? 60 pi epsilon, 60 by pi epsilon sine theta into R power 5. So substitute that here, substitute that here. So 60 by pi epsilon sine theta into R power 5. So this is nothing but ER. So ER multiplied by R square sine theta d phi. So this is equal to what? This is equal to q total divided by what? Divided by epsilon, Okay, so now just solve this integration here, that's it. Okay, now here now here R is constant or not? See, you are integrating with respect to what? Theta and phi. On the surface of the sphere, the variables are only theta and phi. So R is constant with respect to integration. So take it out of the integration here. Take it out of the integration. So what you are going to get? 60 into R power 7 divided by pi epsilon into integral theta is equal to 0 to pi. Integral theta equal to 0 to pi. Sin theta into sin theta, you will get what? You will get sin square theta d theta. Sin square theta d theta. Next, what is left out here? Integration with respect to phi. So integral d phi here, you are having integral d phi. So integral d phi is nothing but what? Phi. Right. Okay, so I am writing that directly here. Integral d phi is nothing but phi. Its range is from 0 to 2 pi. Its range is from 0 to 2 pi. Okay. Okay, yeah. So now okay, so this is nothing but the electric flux. This is nothing but the electric flux that is leaving the closed surface. So this is equal to what you will get here? 60 into R power 7 divided by pi epsilon. So integral here phi, if you substitute the range, you are going to get here 2 pi. And what is the integration of sin square theta? What is the integration of sin square theta from 0 to pi here? If you integrate this, okay, you can check this integration here. You can write this sin square theta as 1 minus cos 2 theta by 2, okay, and you can integrate this. Okay, so what you are going to get? You are going to get, I am writing directly here. You are going to get simply 1 by 2 here. You are going to get simply 1 by 2 if you solve this integration. How you can solve? Just replace sin square theta with 1 minus cos 2 theta by 2. Okay, so then you are going to get this answer here, that is 1 by 2. Okay, okay, yeah. So this is the finally you are going to get. So now here pi will get cancel. So here 2 will get cancel, right? Okay, and sorry, wait, I have missed something here. here if you do this here, if you do this integration, you are going to get pi by 2 here, not 1 by 2. You are going to get pi by 2. You can check that here. You are going to substitute the range now. So once you substitute the range, you are going to get pi by 2. Okay, fine. So now here 2 will get cancelled, pi will get cancelled. So you are going to have 60 pi r power 7. So this is nothing but the electric flux leaving the closed surface. So this must be equal to what? This must be equal to the total charge enclosed by the closed surface divided by what? Divided by epsilon. So from here, what is the total charge that is present within a unit sphere here? They are asking the total charge that is present within a unit sphere. Yes or no? So unit sphere means you have to consider, unit sphere means the radius is what? The radius of unit sphere is equal to what? Is equal to 1. Okay, you have to consider, or you have to determine the total charge that is present within the unit sphere. That means you have to consider r equal to what? R equal to 1. Okay, so now here epsilon will get cancelled. Therefore you will get q total here. Q total is equal to what? Is equal to 60 pi coulomb. Q total is equal to 60 pi coulomb, since here r equal to what? R equal to 1. So this is the total charge here. So this is the total charge that is present within the unit sphere, that is present within the unit sphere. Okay, so I hope it is clear here. I hope it is clear. Understood here? Yes or no? Okay. So the total charge here is nothing but 60 pi coulomb. 60 pi coulomb. So this is the answer for this question. Okay. Okay. So instead of directly giving the electric field and asking to determine the total charge, what they have given, instead of electric field, they have given the potential here. They have given the potential. So from that given potential distribution, we try to determine what? We try to determine the electric field from the relation E equal to minus gradient of V. Right. Okay. So from that relation, we have determined electric field. Once we have determined electric field, then from Gauss law we have determined the total charge. Only 3 steps involved here. I have explained each and everything, the concept behind this problem, so that's why it has taken this much of time. But if you observe, they have given the potential difference, potential distribution, and they are asking to determine the total charge, right? Okay, so what are the steps we have followed? We have determined the electric field. We have determined the electric field from the given potential by using this relation, that is E bar is equal to minus gradient of V. Right, by using this relation we have determined the electric field. Then we know from Gauss law the electric flux that is leaving any closed surface, is equal to what? Is equal to total charge divided by epsilon. Now by using this Gauss law, okay, we have determined the total charge. How many steps here? 1 step and 2nd step, that's it. Okay. Okay. So this is all about this problem here. Okay, so is it clear here? Is this problem clear? Yes or no? Okay. So this is the question I have taken for today here. Okay, so as it is a starting class, I have taken only this problem here. Okay, so from tomorrow, for tomorrow we will see some more concept through questions here, some more concept through question problems. Okay, so I hope this problem is clear. So with this I am winding up this session here. So tomorrow we are going to meet here. Tomorrow we will meet at the same time with different types of problems. Okay, so through that problems we try to understand the concepts behind those problems. Solving the problem is not important here. So you have to understand the concepts that are present behind the problem. So that is what important, right? Okay, so I hope each and every concept is clear in this problem. I hope so. Okay. Okay. Okay, so with this I am winding up the session here for this first day. Okay, so from tomorrow onwards we will continue in the same manner. So concept through questions. Okay, so take care here. Bye bye. So I am ending the session. So take care. Bye bye. Bye bye.